Our third speaker this morning is John Fan. John is from Stanford University, and his expertise lies in the design of metasurfaces. And just as a side note, I want to say that I heard about John originally from Tom Milster, who works closely with John's group, and then Noah independently also recommended John as a really knowledgeable person about this topic, and so I'm grateful that he and his team, some of his team, are here, and his innovative approaches regarding the design are reshaping how we think about metasurface technology and its potential applications in a variety of fields. So thank you, Jonathan.
All right, can you hear me in the back? Yes. Okay, perfect. Well, thank you so much for the invitation. I want to especially shout out Kent for doing such an incredible and careful job for curating this workshop. It's really, I think, the right group of people to be thinking about the future of metasurface applications in astronomy. This is going to be a photonics engineering talk, so to speak, and I hope to do a couple things here. The first is to certainly convey a lot of maybe basic concepts involving how metasurfaces have been traditionally designed. I think we've gotten some really fantastic introductions to how that is done, especially from Noah, and I will also quickly review some basic paradigms in conventional metasurface design using this so-called phased array approach. I want to spend some time discussing freeform metasurfaces designed with the adjoint variables method. I think as we think about more advanced design concepts based on computational algorithms, there are ways to just milk a little more out of what one can do with structured thin film media in ways where we're not going to be breaking physical limits, but that we can start going beyond some of the so-called local approximation limits that Noah brought up. And then for the third part, I want to discuss work that we and others have been doing in machine learning. And it's an incredible time to be doing this type of research and to be thinking about high performance, large area thin film optics in this age. And I truly believe that these type of tools through the development of ideas and algorithms of people in our community, we can actually create something really useful that we can all ultimately use. Okay, so I'll spend the first few minutes talking about conventional metasurfaces. I think Noah did a fantastic job introducing many of the basic concepts, so I will go through this relatively quickly. As was previously covered, I think when one thinks about the term metasurface, at least in the general sense, we are often talking about a thin film type of optic that is subdivided into phase array elements that produce some form of phase response, ideally one between 0 and 2 pi, in a manner whereby stitching together these different types of meta-atoms or phase array elements, one can produce custom wavefront engineering profiles as a function of wavelength, polarization, or other types of metrics in manners that are essentially hard-coded in the phased array design. Given the fact that these are concepts that essentially utilize nanostructured elements or subwavelength scale elements to produce some form of phase response, one can turn to one of a number of concepts for producing these type of phase responses. And these are concepts that can actually be used synergistically together even, so they're not completely mutually exclusive. One way that you can think about producing phase response within a meta-atom is to utilize resonances. These are resonances that can exist in the form of plasmonic resonances or in the form of modes within dielectric resonators. I would say it is fair to say that going from the simple conceptual picture to the physical picture is quite nuanced, but what is often done is that these type of subwavelength scale resonators are often modeled as classical resonance systems. And as we know, whenever we have some form of classical oscillator, we necessarily have a phase response that goes that is associated with the resonance itself. Now, of course, with a single type of resonator, the phase response is typically bounded between 0 and pi. So it is necessary, if you want to achieve 2 pi phase shift, that multiple resonances are utilized. And in the Capasso demonstration from the seminal 2011 paper, these type of metallic antennas were engineered to support multiple resonances, as shown here, where collectively, together with some clever kind of polarization-based filtering, one was able to achieve a 0 to 2 pi dynamic range. It is also possible to utilize multipolar resonances in dielectrics, where some of the most popular concepts involve the excitation of electric dipoles and magnetic dipoles together to collectively produce a so-called Kircher effect, where the interference of far-field radiation from these resonances produces forward scattering with a phase shift that can range from 0 to 2 pi. I think in some ways, with the, let's just say, reinvention of the metasurface concept in 2011, resonances were one of the main ways that people thought about imparting phase shifts in metasurfaces. But ultimately, they have had maybe more limited translational impact simply because of the fact that, as we know with resonances, they tend to be narrow band and also very sensitive to for example, the orientation of the incident field, plane wave, and also are quite sensitive to small fabrication tolerances. And there are actually a number of papers that describe that. Shortly after the initial seminal work, a lot of attention, including a lot of work being done here at Caltech, was placed on dielectric nano waveguides. This is also a concept that was in some ways reinvented based on demonstrations that Philippe Lalonde showed in the 90s. But I would say, as Noah pointed out, the difference between the 1990s and the 2010s was, I would say, just significantly better fabrication capabilities and also a renewed emphasis on concepts involving polarization. The idea here is that instead of thinking about resonant elements, we're going to be thinking about phase shifters, where we will be thinking about these type of waveguides as phase shift elements. And the way to think about this in this simple tutorial example is that if we have, for example, a narrow piece of silicon here serving as a waveguide, and we vary the width here, this waveguide will essentially support an effective index that varies as a function of waveguide width. And this variation in effective index can be understood if we look at the modes of light coupled into these waveguides, where if you have, for example, a very thin waveguide, you have a lot of mode leakage, and more of the mode is in air relative to silicon, and so you have a very small effective index. And as this waveguide becomes wider and wider, more and more of this light becomes confined in the waveguide, and the effective index response is therefore much higher. And as such, if you create a library of these type of waveguides and stitch these together, you essentially can produce something that has a type of wavefront response that is non-resonant. And here we can kind of see, as we consider the design space of these type of nano waveguides, that ultimately with your library of different structures and arranged with different packing fractions, it is indeed possible to cover a range of structures that exhibit both high transmission and the requisite phase responses necessary to achieve arbitrary wavefront control. Another concept, which is very powerful and really the basis not just of geometric phase metasurfaces, but also a lot of what we have seen with liquid crystals, is this concept of geometric phase control, which is essentially a concept that utilizes these types of anisotropic birefringent media in order to produce phase responses. As Noah showed, the idea here is to consider a small-scale waveguide, a subwavelength scale waveguide that essentially acts as a half-wave plate. It is capable of converting, for example, one-handedness of incident polarized light and converting it to a different handedness. And with geometric phase, what arises is that there's a net phase shift that arises based on the relative angular orientation of the wave plate. So we can see here, for example, that if we consider these subwavelength scale birefringent half-wave plates and we vary the orientation, what we actually get as we look at the conversion in this case of RCP to LCP light is a traversing of the Poincare sphere across different paths that are a function of angle, and that the geometric phase can actually be visualized as an area relative to a reference that is essentially earmarked and taken by these different types of paths. So it's a very interesting and powerful concept because it is very robust, I would say, and it has been something that has been exploited with considerable, in large part to communities that have been lasting many decades working with birefringent media and liquid crystals. Ultimately, what I've shown are just the very, very basic bare bones concepts in conventional metasurface design. And there's been a lot of work to essentially engineer meta-atoms and elements to achieve various types of desired responses. There's been a lot of work with broadband metasurfaces where the idea is to essentially dispersion engineer, for example, waveguides in a manner where the effective index of those waveguide responses are more independent of wavelength. And ultimately, you can imagine that this concept of dispersion engineering can also lead to variations, intentional variations of phase response as a function of wavelength. We can see here in this example of a broadband meta lens that essentially operates from around 1300 to 1650 nanometers. I think in general, a lot of the practical demonstrations have shown broadband meta optics operating on the order of half of an octave. In some cases, some people try pushing this towards an octave, but one is ultimately limited to the ultimate realistic fabrication capabilities of how large of a high aspect ratio structure you can actually realistically make. And ultimately, there are physical limitations to how much you can actually dispersion engineer an axially symmetric type of structures. I think there's a lot more work thinking about metasurface systems where we start thinking about having, for example, stacks of metasurfaces that I can collectively produce, for example, broader band responses, maybe not completely unlike or at least analogous to what is being done in polarization optics and the collection of wave plates in a manner that can produce broadband polarization responses. So in any case, this has certainly been a topic that has been studied quite a bit. There's a lot of work on narrowband metasurfaces, which are so-called non-local metasurfaces. These are devices that are effectively transparent to incident light, and except for a narrow band of wavelengths, where for a very narrow band wavelength, the incident light will couple into guided mode resonances within these structures. So these typically can have quality factors ranging from tens to thousands. And in terms of having a type of optic that can essentially serve as kind of a spectrally or polarization selective beam sampler, that potentially could be of interest to to this community. And then there's a lot of work on polarization analysis, a lot of which NOAA has done, and certainly I think this will be a big topic of this workshop. Okay, so I think for many types of applications, the conventional metasurface paradigm actually is extremely effective. And I would certainly say, if you can do it this way, you should do it this way. There are considerations, for example, in robustness, which I don't think have been analyzed nearly enough, where it actually turns out that stitching together meta-atom structures actually turns out to be a very robust way to produce experimental metasurfaces that are a little more immune to fabrication errors compared to what I'm going to show you. With that said, it is also clear that conventional metasurfaces have limits, some of which were presented by Noah, where these metasurface concepts do assume multiple assumptions about multiple types of local approximation assumptions. And as such, these type of concepts, while they are effective in certain types of regimes, and in this particular case of a very basic system, we're looking here at a Blaze grating. We can see here that these type of conventional concepts work very well, for example, at small deflection angles. If you push these concepts to regimes of discomfort, like, for example, large angles of deflection or other types of regimes, these concepts start to a lot of the assumptions that we make in terms of the phase, in terms of the interaction between these meta-atoms start to break down. And as a result, the efficiency of these structures reduces. And so there's a very natural question as to whether these are physical limitations in terms of what thin film optics can do, or if this is a limitation to the meta-atom paradigm. And the answer, at least in this particular case, is that these, for some cases, are due to limitations in the meta-atom paradigm. And we can see here with freeform optimization that it's actually possible in the case of a Blaze grating to find ways to break the limits of efficiency at large deflection angles. And these are also concepts that can extend to other types of figure of merits. Now, there are many types of freeform optimization. There are gradient-free concepts such as genetic algorithms, particle swarm optimization. What I want to talk about today is a gradient-based form of optimization termed the adjoint variables method, which perhaps like everything else talked earlier this morning was developed decades ago, but was introduced to electromagnetics in the early 2000s by Ole Sigman from a professor at DTU who was actually applying topology optimization to mechanical metamaterial systems, and Eli Jablonovich from Berkeley, he was at UCLA at the time, who was also applying topology optimization to photonic crystals. And as you can imagine, this is a very powerful concept that has, over the last decade or so, bled into metasurfaces. I'd like to talk about a bit on how this works, and I would like to refer to Owen Miller's dissertation. Owen is a professor at Yale, as a really outstanding reference to really, and well-written reference to really explaining the concept. And what I'm going to be showing is something that is a little more qualitative and conceptual, but I would certainly refer you to Owen's dissertation if you want more details. And to understand the adjoint variables method, I want to pose the following question. Given a normally incident plane wave, what type of structure can maximize the field intensity at point R, right here? And as you can imagine, this particular objective is essentially an attempt to design a lens, but you can also imagine that instead of simply looking to maximize intensity at this single point, you can maximize intensity at different points. You can maximize intensity along a line of arbitrary wavefront shapes. So, and this can all be done through superposition. So, so if you understand how to maximize intensity at a single point, you actually understand how to perform arbitrary wavefront transformations. I want to just massage the math a little bit, reframe this objective and pose this as how can we maximize the figure of merit f, which is going to be defined as 1/2 e squared, which if e squared is maximized, then 1/2 of E squared is also maximized. Now, there are a number of ways to address this problem, and I want to start out with a way that is not efficient at all, but gets the point across, which is that we want to consider a gradient-based approach to optimization. And what we're going to do is we're going to consider perturbations to this area, which is our device, in a manner that increases our figure of merit. We're going to index things where points inside of our device are r-primed, and the point here where we want to maximize the intensity is r. And we're going to be calling this incident field, we're going to call electric fields or electromagnetic fields produced from this incident field both in the device and at this point as the forward field. So one way that we can think about a gradient-based approach to optimization is to essentially divide our simulation domain into a grid. This is a very fine grid with on the order of lambda over 20 to lambda over 100 resolution. And we're going to ask ourselves, does a small perturbation at, let's just start here at voxel 1, lead to an increase or decrease in our figure of merit in a manner where we can decide to push this dielectric constant towards silicon or air? So we're going to add this dielectric perturbation, and we're going to see if the electric field here is larger or smaller than what it was previously. If we look at the figure of merit and we make some quick approximations, we can see that the change in figure of merit, if we add this dielectric perturbation, is approximately this product between the forward field and delta E, which is to say, if you add this dielectric perturbation and you get an increase in the electric field at this point, this is positively signed, and delta F is therefore going up. That is a good thing. But if you add this dielectric perturbation and this goes down, this has a negative sign, and delta F actually goes down. So we can see here that, that we essentially have a way to calculate gradients. We can add this perturbation, compute the figure of merit based on this delta E, and decide if we want to add this perturbation or ultimately subtract this type of perturbation. Okay, we can do this for each and every voxel, and you can imagine that in a typical domain there might be thousands, tens of thousands, if not more voxels, and that's a lot of simulations. It's in fact so many simulations, not even a PhD in astronomy can wait around to get this to finish. So it's, I would say, an intuitive way to think about gradient calculations here, but it's not a practical way to go about things here. So what can we do that is a bit different? And to introduce maybe a better way to go about this, I want to consider the following, which is that we talked about this voxel being extremely small and this dielectric perturbation being a perturbation. And so we can actually approximate the interaction between this perturbation and this incident field as a dipole excitation, where the excitation of this dipole and its propagation and the propagation of the resulting electromagnetic waves to R is linked using this Green's function. And so this is just very basic. If you have a point dipole and you want to know what happens to the radiation, there's a Green's function to describe that. And this Green's function is a function of just the whole domain. Now here's where there's a very nice symmetry property that we can exploit to simplify all this. The Green's function is symmetric, which is to say that GRR prime is equal to GR prime R. This is a manifestation of Lorentz reciprocity, which essentially tells us that the excitation of a point here and the measurement of the field here, and the excitation of a field of a dipole here and the measurement of the field here will actually lead to the measurement of the same field. And that is extremely interesting. It's also the basis for wireless communications as we know it. In this case, we are using and exploiting this centuries-old concept in optimization. So in order to therefore calculate how a perturbation here can produce a change in the figure of merit here, we're actually going to leverage reciprocity and put what we are going to be calling an adjoint source, or in this case, an adjoint dipole here, and we're going to measure the field here. And what we will actually find is that the same adjoint field can actually be used, the same adjoint excitation can be used to compute the change in figure of merit from this point here for all voxels, as shown here. So this is quite incredible. Actually, if we want to understand how the dielectric at every voxel in this device can be perturbed in a manner that enhances our figure of merit, we actually can simply do two simulations. One is a forward simulation, where we measure the electric fields everywhere in here, and one is an adjoint simulation, where we have this excitation and we measure the electric field everywhere. We can calculate the product of the adjoint and forward fields at all voxels, which are achieved using only two simulations, and through that we can calculate calculate changes to the figure of merit in a manner where we can use this in a gradient-based optimizer. So therefore, if we incorporate all this into a gradient-based or stochastic gradient-based optimizer, this is what we have. We have an iterative algorithm where you start with something random, you get to a final design. For each of these iterations, you do a forward and adjoint simulation. You use these simulations to compute perturbations to the dielectric constant at every voxel in your device in a manner that improves your figure of merit, and you eventually can converge to the final design. So this is what it looks like. This is the top view of a metagrading that is intended to be used as a large angle beam deflector. And we can see the dielectric constant within this structure evolving and being perturbatively pushed in a manner that leads to an enhancement in figure of merit. And there are a lot of bells and whistles, as you can imagine, in an attempt to control feature sizes in order to make this as robust as possible, et cetera. And what you end up with is now a very non-intuitive structure that is able to exhibit high deflection efficiency. We've done a lot of reverse engineering to understand why this happens, and I think when we started this, the hope was to find maybe some design rules that we can use to generalize to producing high quality structures. But what actually turns out to be the case, and maybe as predicted, is when you have these freeform structures, you end up, this enhanced performance arises because you have structures that can support more complex distributed high order modes. There are scattering properties where incident light will not just propagate through and exit, but it will actually bounce around and exchange energy between these different modes. And ultimately, using computational design, you are engineering interference between all of these different channels for all of these different modes, where you get constructive interference in the desired direction and destructive interference in all of the other channels. Okay, in the last few minutes, I want to tell you about, I think, where this field is going. It is impossible to talk about, to talk about anything these days without talking about machine learning. I think, in fact, there's rarely an issue of the New York Times or the Wall Street Journal where there's not something about machine learning, and we all know how disruptive or maybe how much of a value add it is for our own teaching and research. These types of tools, like ChatGPT, are very powerful, but they're not quite good at solving scientific problems. I know this because my students who take my E&M classes come to office hours asking why ChatGPT is not giving them the right answer to their homeworks. So it's at least not there yet. And the answer, and the question that I want to pose is, is there a way to get this closer to a way where we can ask, if we can ask ChatGPT for restaurant recommendations, can we also ask it to help us design metasurfaces? And the reality is, and it's something my group and many others have been working on, is there are many areas where machine learning can be a huge value add, but it's up to us to really tailor these algorithms to help us understand the calculation of performance bounds, to help us do optimization, to help us accelerate simulations, to help us fabricate devices, especially freeform devices, better. But ultimately, it's all coming together. And if there's one takeaway that I see, ChatGPT has only been around for, what, 3 years? And look how disruptive it is. And if we really commit as a community to developing these tools, and we ride the wave of CS and hardware for machine learning that will clearly continue to be developing at an exponential rate, we can really create useful things for us. I think kind of a foundational area where machine learning will have a major role are in solving PDEs. There are various ways to do this, so-called physics-informed neural networks, the use of Fourier neural operators. We like the neural operator approach, and specifically in essentially using neural networks as a true full-wave surrogate solver, where we have an input geometry and we get output fields. One of the keys here to get this to work well is you have to train these using a combination of simulated data and physical loss, which is to say you have to train these with Maxwell's equations. And if you do this, what you get out are not only accurate fields, but fields that have accurate derivatives, spatial derivatives, which is very important for actually using these fields in practice. One of the biggest challenges as we think about accelerating E&M solvers, which, by the way, for what I showed there, you can get a 2 to 4 order of magnitude speed up in solvers, is to understand how to adapt machine learning tools to solving a wide range of problems, which is, I would say, one of the real pain points of the technology. So this is where we've looked into and have taken inspiration from methods in domain decomposition, where the idea is to take large arbitrary domains, split them up into small subdomains, and to train neural networks, not just one, but a set of neural networks that can solve collectively nearly arbitrary boundary value problems. And then in doing so, one can iteratively find self-consistent solutions where the solutions to all of the subdomains and their boundaries agree with each other. If you do this, and if you also continue to innovate neural network architectures that are tailored for these type of concepts, you can get these boundary value PDE solvers to operate with well over 99% accuracy in a way where this is almost a true substitute for a ground truth solver. This is just showing the range of subdomain simulation problems that can be solved. And with this, we can solve large scale, or at least larger scale problems that are a few times the wavelength. Here are the structures with arbitrary sources and boundary conditions. Here are the ground truth simulation results. And here are all neural network-based PDE solutions solved using the iterative short-spaced domain decomposition method. Neural networks can also be used for optimization, where, seeing the time, I will simply say that generative networks can actually be used as an optimizer itself to perform global optimization. One of the big challenges in optical design is that we are talking about non-convex design spaces, which have lots of local optima, some which are good, some which are bad. And it turns out that if you use a neural network and you train these neural networks, these generative networks, with physics, that you can actually overcome some of these local optima issues. And the origin of this is that instead of directly training and instead of directly designing physical structures, you're actually optimizing weights in a very high dimensional space. And that actually helps overcome many of these local optima, where local optima in the physical space may look like saddle points in the neural network space. So these are concepts that have been that we have shown to be more effective than lots of even, hundreds of local optimizations. These type of global search techniques, I think, will just get us to numerically finding practical bounds to what nano optics can even do. Okay, so in the last couple of minutes, I know Kent asked me, well, this is great. I want you to tell us about what design, not only concepts in design, but what does it look like in practice? And I know I've shown a lot of pretty pictures, a couple of movies. Here's the reality. I think for my group, and I think for many of you sitting in the audience, engaging in the practice of photonics design is a rather labor-intensive process. It requires having a background in programming. It requires spending often weeks, if not months, learning how to use one of a number of simulation packages, searching the internet for good open source simulation packages, finding limits to a lot of simulators and optimizers, given that every time there's a hardware upgrade or a neural network upgrade to something, things that are hot 1 or 2 years ago just become obsolete. And so this is something that my student Robert, this is kind of a traditional and I would say typical workflow of what someone like him has to do to get the results that I showed you involving freeform optimization. It's more than just a couple of simulations, right? And it's a task in itself. And I would completely understand, for example, that say someone at NASA or JPL may not want to invest all of this time necessarily to do all of this. So I think this is where the era of large language models is incredibly interesting, where I mentioned a few slides ago, can we make ChatGPT-like interfaces? And so I literally want to, ask the question, can we actually make a ChatGPT-like interface where often a lot of what we want can be described semantically, right? Together with a few equations, together with ideas of design constraints or fabrication constraints. And there's no reason in today's world why a large language model couldn't take that information and manifest it. And so here we have looked into prompt engineering, a large language model, together with all of our high-speed simulation and design tools, together with interfacing of various types of computing packages, experimental materials, databases. Also, it helps that, with these large language models, they can read every paper ever written about metasurfaces, at least those not behind a paywall. So in terms of what this can be, and I realize I'm out of time, so this is a real-time video of a trained large language models where we have asked it to design a lens, a meta lens, using freeform optimization. And I think the idea, what we clearly see is that it is just a matter of time where what we often do as very labor-intensive exercises will eventually be fully automated. And the use of neural network surrogate simulators and optimizers not only will give us accurate solutions, it will also give us solutions. It will also accelerate things where we will be able to innovate almost in real time. And I think that's something that for anyone who has done any form of design, you're often going to lunch waiting for full wave simulators to crunch numbers, or you start some job and come back after the weekend, and that's not how it should be. And I think it's already getting to a stage where for a number of different types of metasurfaces, we can fully automate these things. It turns out actually ChatGPT does have an understanding of what focal length, and it does know some basic equations. And I think maybe I've bought this enough time where we have here now the GDS file for a fully optimized freeform meta lens that we can just take for fabrication. So this is, just to be clear, very much a hello world moment This is not a tool to be used for all of your problems, but it is also clear based on, I think, what we have done and what we have seen and what we project, that this is where things are going. And I think it's actually communities like the astronomy community that will be particularly the real beneficiaries of this type of technology, where I know it is a community that understands a lot about optics. Maybe it is interested in nanophotonics, and here we can just create this bridge. All right, so I'm well over time, so I'll just put this up, and thank you for listening.